analysis of this phenomenon. That is, if I know some concentration of the protein on the right side, how much the pressure can be generated. So that's the next goal. So we can just rewrite this these PowerPoint slides in here by kind of drawing a, let's just say this is a semi-permeable membrane where the water can actually go back and forth easily. Okay. Now on the left-hand side, we have basically pure water. Now this right-hand side, we have water. Now we started dumping into a bunch of proteins. So these proteins are, just representing a big ball. So they cannot go through. So this is the situation that I'm just redrawing over here. So since water is going through freely by itself, so before you add any protein to it, so clearly at the pure state, the pure water, let's call this left side, the right side, they will be equal. So nothing will happen. Just like the membrane doesn't seem to even be there, right? Now, all of a sudden, I start add protein into it, or any other molecule that cannot pass through the membrane. Now, so the result of this is that, so at the beginning, this could be the same level because they're just hydraulic pressure be the same. Now, when I add the protein, I can call protein P. So much so that if I add protein to it, the protein's constant molar fraction will be XP. Just that's the protein I add to it. And so now, then the water's, the molar fraction will be XA, which is actually 1 minus XP. Right? So this will become useful later at the moment. All right, so what is the chemical potential to the right chamber on the right side now after I did this? Now I'm going to ask Jerry. So can you tell me what is the chemical potential now in the water related to the pure water?
So the chemical potential with water pure plus the Ln of the molecule.
Yeah, I was ahead of you. I was thinking you were going to say that, but then I wrote. Okay, good. So you finished the sentence. That's basically what it is. So as a result, the water will flow from left to right because I still can't see your mean you. Is your name? Like you said by the Jerry. How does Chen, yeah. So why now all of a sudden water is going to rush from left to right? We said something earlier, but I want you to look at the formula, using the formula to explain to it. Which says the general reason why. So the left is still pure water. Now the right side is no longer pure water because we start dumping protein into it. The protein has a molar fraction XP, the water molar fraction becomes XA. The chemical potential of the water to the right side become related to the pure state by the RT-Ln XA. Now, so we already talked about at the very, very beginning that the water will try to rush from left to right now, all of a sudden. Can you explain by looking at the formula? It's actually not very complicated. So we said something about matter will, we already told you the answer. The matter will move from high chemical potential to the low chemical potential, right? So now the left-hand side of the chemical potential is the pure. The right side is now the pure plus this term. Now, is this term positive or negative? It's positive. Diego, I noticed you raised your hand. What do you think? Yeah, so it's actually negative because this molar fraction is less than 1. So that's what happens. So I'm just trying to keep everybody on the same pace as we're thinking along. I kind of repeat what we discussed, but I want everybody to see them in a different format. We had some general discussion. Here is the reason why. So now we actually create a difference. Diego?
I had a question about,
Yeah.
so the water molar fraction, are you saying it's molar fraction of 8 times 1 minus molar fraction of P?
Oh, no.
Yeah.
No.
It's
Those
equal.
are basically, is
Equal,
just,
okay,
yeah,
yeah.
equal. Yeah, I was put a parenthesis, but you can also think of it as being 1 minus x.
Yeah, okay. Sorry.
Right. Everybody with me together? So we basically create a gap. The gap is this pi is higher, the chemical potential. This chemical potential is lower. By how much? By this. No. So therefore the water try to go. They try to go there. But we also know we're living on Earth, right? So that's what happens when you live on Earth. So the water try to go, and then you have gravitational pull. That's where the pressure comes from. They have to really. So the pressure actually can start to try to push back them down. So eventually you get it to a point where the water is not going to rise anymore. Or you can think of something like this. Okay, the water is trying to go, but I won't allow it to go. So I have to apply a static pressure to the right side to prevent it to go. So you can think of osmotic pressure that way. That's probably a better way to think about it. So the water try to rush because of this. Yeah, with me? Okay, so now I don't want them to go because I know they're going to go. If I don't, they're going to eventually just rise up like this picture is shown over here, right? No, but so that's the sort of osmotic pressure. That's the source of it. Now what I want to do is I want everybody work together. Can we find a way to calculate the osmotic pressure if I tell you how much protein I put in there? So that'll be very useful thing to do, right? So that's the purpose. That's the focus of today's class. Now this actually is much simpler than the boiling point pressure, or no, boiling point or freezing point change, the mathematical. So basically, this is what So what happened here is that the left-hand side has a chemical potential of this. The right-hand side has a chemical potential of this. So basically, the difference, this one is higher than this. If I want to, this is the right side. Basically, I take this one, subtract this one. I could just use this term like this. It will be minus. Right. So that's the gap. Even though it looks minus because this is a negative, so it's a positive term. So the left chemical is higher by this amount. So I want to make it up. And so when we discuss the freezing point, depression, or boiling point elevation, we use one of the two parameters to make up by temperature. Now I'm switching this because we're trying to explain physiological phenomena of what we refer as hypotonic, isotonic, hypotonic, which is pressure. So obviously, what I'm trying to do right now is I'm going to make up the difference. This time, the two previous collective property about freezing point depression or boiling point elevation, we compensate this term by temperature, which is kind of complicated because, as you show in the demonstrated video, and in fact, Teddy and I talked about it. The hard part is the T temperature T here, so I had to do some maneuver to move the T over to a relatively complex differentiation and calculus. Now here, since it should be a little bit straightforward. So now I'm going to ask, what do we do? So now we're going to apply pressure to the right side. So So what is the quantitative relationship that we have learned in the past that can be used to establish or to produce a energy or gives energy change to make up the difference. So anybody? I'm going to ask Nick. I know Nick was trying to. Are you using a cheat sheet? So what do you think we should do here? So what is the sense? So I'm apply pressure to the right side.
Can I ask a quick question?
Sure.
Sorry to interrupt. Shouldn't, if it's final minus initial, wouldn't you want to do right minus left? Right, if it goes to the right side?
I'm trying to go.
Oh, you're just looking at the difference between.
Yeah. So I'm
doesn't matter.
I'm higher than it. So I'm going there because I'm higher than that, but I'm now. I know that one is so low. I'm not even trying to do that. I'm going to prevent. So I'm going to raise the chemical potential to the right side by making up this difference.
Okay.
So
Got it.
As you see my video, this is a little bit mind twisting, but if you actually sit down and think carefully, it's actually not that hard. It was just, I'm trying to make up the difference because this left side is higher than the right side by this much. Now I'm trying to raise the right side only by this much. So Nick, what do you think we can do?
I'm thinking of some equation we use that the change gives energy to the change in pressure.
Okay, so that's good. So that's basically, yeah, that's all you need to say. You don't even have to write out the equation because I don't, you can imagine you remember this 20 years later. I mean, but all you need to remember is there's a trick for the gift energy can always be altered by temperature and pressure. And then you just need to go back to your online or you could look up the cheat sheets. That's it. So, but now I do want someone else. Anybody who have their cheat sheets in the head at the moment? Yes, Eric?
VGM equals VM dP.
Okay, yeah, so basically we have discussed VdP minus SdT. Now, since we're talking about chemical potential, we really do mostly the molar, and sometimes we just simply write it down. Right? Now, when we do these sort of discussion, we can reasonably assume that we're going to, now we don't change temperature. So, you know, you can imagine that where in the biological system, the temperature is not what we're going to change. Rather, we'll fix it. So, or for any other reason. So we're going to fix the temperature. So then, basically, you can change chemical potential by the molar volume of the solvent, so or the solution. Okay. So that's basically that's good news. Basically, it's not that hard. It's like, okay, then how do we actually change? Now, how much pressure do we have to change to make up the difference? So that's the thing we want to get at, right? So, but then how do we do? This is something like, well, I add a tiny little pressure change, I can cause some change. But if I change chemical potential over a range of pressure, what do I do? Integrate, right? Okay, so I'm going to change. So each side has initially have pressure, but now I'm starting to apply some kind of pumping system. I start to pressure add something. They use this term called pi. So basically, I'm starting adding to the point where the water do not really go. Otherwise, it will go. So that means somehow I have changed the chemical potential from the pressure P to a new pressure. Now, so what happens if I start apply pressure to the right side? Before I do any math, what is is the chemical potential increase or decrease? Because what really confuses us earlier when we talk about the boiling point or freezing point is we got confused because whenever we add temperature, we actually drop the chemical potential. And this is who can drop first. Now here, what happens if I add pressure to this? Is increase or decrease? Got it?
Wait,
So the chemical potential of water in the system, if I
Yeah.
start add pressure on this, is the chemical potential of water increase or decrease?
oh, increase.
Why? Look at the formula. Do you see anything has a negative volume?
No.
Okay.
So increasing pressure.
So
is
in
just a
the
positive
entropy, we have,
change.
when we talk about this, we have minus Sm, so that's the, which you get us really confused. So here, always, when you apply pressure, you increase the Gibbs energy, or molar Gibbs energy, in this case, chemical potential, right? So that's one qualitative analysis. The other thing is, we can reasonably assume a couple of assumptions. For example, the molar really is a mix of solution. You know, if you start dumping protein into the solution is no longer pure solution. So is the molar volume of a protein-containing solution the same volume as a pure water? Well, maybe not, but they're so close. You know, the amount of protein added is so tiny. So you could simply say this is basically of the pure molar volume because it's very dilute, protein or solid into it. That's something. We can make a reasonable assumption. The other assumption is that, so if this is the case, they can also be constant. Now this integration becomes very convenient, unlike the other one. So if this is the constant, that's pretty simple. So if I start apply pressure to the solution, I'm just increasing the chemical potential by simply just one of the constant molar volume times P plus pi minus P is pi. Okay, so somehow when I start add enough pressure, whatever the new pressure I'm adding, I'm causing the chemical potential change, which is, you can call this chemical potential at the new pressure minus originally pressure. Well, basically you're trying to integrate over the range of the pressure difference, and then you started to apply the formula into here, and then that basically, you cause chemical potential change simply by whatever the pressure times molar volume of the solution. Austin?
So we're just assuming that the protein itself makes no contributions to lower.
Yeah, there are like the amount of protein solution we're dealing with, usually like you're talking about milligram per mil. Like you can't really dissolve a lot of protein in solution. They're so tiny, both in terms of the mass or molar concentration or molar fraction. They're just very minuscule. So this is the amount you can increase. So what I want to do, so what this should be make equal to, Natalie? So what do I do now? So now I know that, I know this is what the amount of chemical potential I can gain by applied pressure. So what is this trying to make up? So how should I set up this to be equal to?
What are we trying to say?
Like, so we're trying to figure out how, when I add enough protein to a certain concentration or cause the molar fraction of the water to be smaller, so then I have a chemical potential energy deficiency on this side. So now I'm trying to increase, I can show that if I increase pressure on the right side, I can cause chemical potential increase on the right side by these formula. Now, how should I, what is this trying to equal to cause the water not to flood to the right side?
Pure
Yeah.
chemical potential of the water? Like,
The pure or the pure to the right side, or is it some sort of difference? Like on this board, there's another term that.
the negative RTL and XL.
There you go. Yeah. So this guy has to be making up this. So sort of the one Kalia earlier you said. So basically, what we're doing here is I have a gap here. I'm just increasing the size. So this guy. So this sometimes if you actually worry about what are we doing here. So well, basically this is the positive term. I'm going to trying to pumping up the chemical potential by just grinding on the pressure to the right side. So the more grinding down you do, you raise the chemical potential, and then whatever the entropic caused problem, the chemical potential lag, the difference, now all of a sudden I'll make it up. So that's basically, so it's pretty simple mathematically. This one, the mathematical skill technique used to solve this problem is actually relatively simple compared with the boiling point elevation or freezing point depression. So in this case, you just simply say, okay, all right, so the pressure, extra pressure I'm going to add times the molar volume has to make up. And this obviously is a positive term because this is smaller than 1.
Yeah, so my confusion though is because there it's mu of p plus pi minus mu of p, which is basically right minus left.
Yeah.
But over there you did left minus right.
Okay, so the left is higher than the right side. So, okay, let me do this. Mu L minus mu R equals mu pure, because left is pure.
Yeah,
right?
yeah, yeah.
The right side is pure plus RT. Make sense?
Yeah.
Then this guy is canceled.
Yeah, no, that derivation makes sense, but when you're then setting it equal to pi Vm,
Which is confusing, huh?
yeah, just because you did, because up here it's like
Okay.
it's like left, it's right minus left.
Oh, so I'm not
DC.
trying to do that. Yeah, I'm trying to show the gap, the difference.
Okay.
This is high down here by this much.
Uh-huh.
Now then, this left side I'm not doing it because I'm not applying any more pressure. So I'm now trying to elevate this side by the same amount. So then eventually they're going to reach the same level. So then the chemical potential to the right side will start to have this extra turn. So then they will make up the difference. Does that make sense?
Okay, yeah, I think so.
Actually, I used the same thing when I derived the boiling point elevation in the supplemental video.
Oh, so yeah, it's the difference of this side is
I'm
currently
trying-
this.
Exactly.
And then the difference of this side we want to make.
Yeah, so this side is
this.
lower. Now
So
I'm
it's
adding
the
pressure.
same.
As I add pressure, it starts eventually catch up to that.
That makes sense.
Does that make sense? Okay. Now, so here I would have to use a little bit of a math tool here.